Okay, up to this point you should have a pretty good idea of how to calculate the area under the curve using the limit of a Reimann sum, which is what this expression here is. We take a rectangle, we take n rectangles in fact, we multiply our length times our width, which is our y value f of x times our width delta x, and we sum n rectangles up through the summation k from 1 to n, and then we do the limit of that. And if we do that, we get the area under the curve between x equals a and x equals b. Now what I want to introduce today is a replacement symbol for that called the definite integral. So this symbol is replaced by this symbol. Now of course that looks like the integral sign for indefinite integration, which we've already talked about, but at this point you don't want to think of it that way. You just want to think of this as a replacement symbol for this. Alright, and there's sort of parallels, as you can see. The limit of the sigma, the limit of the sum, is replaced by the integral sign from a to b. The f of x is f of x, and the delta x is dx. Alright, so the next thing we want to do is make our understanding of this symbol, the definite integral, just a little bit more broad than it is at the moment. Up to this point, we've always talked about the function being above the x-axis, like so, and calculating the area under the curve, which, if we have f of x and dx, f of x is a positive quantity, dx is a positive quantity because it's calculated by taking the end minus the beginning divided by n. So when you sum up these rectangles, you're going to get a positive quantity. So we recognize this process and this symbol as the area below the curve between x equals a and x equals b. But what would happen if the function was below the x-axis? So let's just draw something like that. Here's f of x, and bounded by x equals a and x equals b. Alright, this symbol would represent what? Well, f of x would be the height of the rectangles, which in this case would be negative. Dx would continue to be positive, because we're going from the end to the beginning, so b minus a over n is still going to be a positive quantity. And so if we sum up, which is what the integral sign means, all of these rectangles with a negative height and a positive width, we're going to get a negative value. Okay? And you say, well, what does that mean exactly? Area is always positive. So what we're actually going to get here is the opposite of what this blue area is. And so in general, if the function is below the x-axis and we do our definite integral, we get the opposite of the area between x equals a and x equals b. Just to go one step further in terms of making that clear, if we happen to know that this area was, let's say, 10 units squared, then what I'm saying is that the definite integral between a and b, the left to the right, of f of x dx is negative 10. Okay, it's the opposite of the area above the curve. Okay, so we're at the point now where we want to come up with a generalization in terms of what the definite integral means. And so let's suppose we have a function that's a bit above and a bit below the x-axis. If I were to look at this and I were to calculate the definite integral from a to c, from left to right, of f of x dx, because f of x and dx are both positive, I'm summing up positive quantities, and so that would be 5. If I was doing the definite integral between c and b of f of x dx, because I'm summing up negative heights with positive widths, I'm going to get a sum which is negative. So this quantity here represents negative 8. And so if I want to know the integral from a to b of f of x dx, that is simply the sum of the integral from a to c and from c to b. Okay, the integral flows, okay, a to c, c to b, and so this is 5 plus negative 8, and so we get a quantity of negative 3, okay, which we call the net signed area. So in general, this integral represents the difference between the area below the curve to the x-axis and the area above the curve to the x-axis, called the net signed area. And as with anything new, we always want to look at how it works and what we can use in terms of properties. So a couple of important properties. The first one saying that if you have a function which is continuous, okay, notice the word differentiable is not there, so I could have a cusp on my interval. It's saying that we can do this. This function is integrable. Okay, remember that doesn't mean anything to do with anti-differentiation at the moment. It just means we can find the net signed area, which makes sense. I should be able to find the area under that curve. Alright, we have a number of other properties of the definite integral. If I integrate from 0 to 0, net signed area between 0 and 0, you would make sense that it should be 0. There is no area. Alright, here's an important property. The integral from a to b of f of x dx, keeping in mind that dx is calculated by the top of the integral sign minus the bottom over n. And if this is to the right of this, this will be a positive quantity. So if I were to reverse the order of these limits of integration, as they're called, that would cause the sign of dx to switch. And so that should cause the value of the entire integral to switch. So these two integrals are related by the fact that they are opposite in value. Alright, property 3 is simply saying that for a definite integral you can split it up and pull the constants out. We've seen many properties like that before. Number 4 says that if you have three numbers on an interval, then you can break the interval up into parts, which I did on the previous page. And the interesting thing about that is that C does not necessarily have to be in between A and B. As long as these three values are all on the same interval, this property holds. Properties 5, 6, and 7 are fairly straightforward, I think. Please read them over, and if you have any questions, we'll discuss them in class. Alright, let's interpret a couple of definite integrals and evaluate them. So in this first example, I have an absolute value graph that I'm working with. Has a vertex at 2, 0, so it looks something like that. And what I'm being asked to do is calculate the net signed area between 0, x equals 0, and 3. And because the graph is above the x-axis, f of x will be positive, dx will be positive because we're going the higher number minus the lower number to calculate it. And so the value of this definite integral represents the shaded area in red. Well, because this is a shape that I recognize, I could actually calculate that area simply through the use of area of a triangle. So I have half the base times the height for this section. So that would be 1/2 a base of 2 times a height of f of 0, which would be 2, plus this triangle, 1/2 a base of 1 and a height of f of 3, which if I plug 3 into there is 1. And so I can evaluate this as 5/2. So please note here that in terms of doing definite integrals, which remember represents the limit of a Reimann sum, we don't have to necessarily go back to breaking everything up into an infinite number of rectangles if the area that we're finding is something we already know how to find the area of, which in this case we did because they were triangles. Alright, let's look at a second example. I'm going to do the definite integral between -1 and 1 of the square root of 1 minus x squared dx. Alright, so our first job is to want to recognize, if we can, what this graph is. So we have y equals the root of 1 minus x squared. And you could reorganize that, square both sides, and hopefully eventually realize that what you're dealing with here is a circle of radius 1 So it looks like this, and it's the top half of the circle because it's just the positive square root. And so our definite integral f of x times dx, this is one particular rectangle I've drawn here, dx being a positive value, right minus left over n will be a positive value, and so the value of this definite integral will be positive. It'll be this area. Now again, we don't have to break this up into rectangles because we know how to calculate the area of such a shape as the area of a circle, half circle, so it's 1/2 pi radius squared, and so the value of this definite integral is pi over 2.